Hello, and welcome to our next lesson in electrochemistry, in which we're going to learn how to use the standard reduction potentials chart, which is chart H in your reference pack, to calculate the electrical potential or voltage of a cell. This electrical potential is sometimes called the EMF, or electromotive force. And this is another way of looking at the spontaneity of electrochemical reactions. So as we learned in the previous lesson, voltaic cells are going to produce electricity because we have a spontaneous reaction occurring. And remember that spontaneous reactions meant that the delta G naught was negative. It was less than zero. And since electricity is being produced, this gives a positive voltage. So the EMF, or the E naught of the cell, which is the list of electrochemical reduction potentials that you see in the next on chart H when we get to it, has to be greater than zero. And so these mean the same thing. A delta G naught of less than zero and an E naught of greater than zero both mean a spontaneous reaction. For an electrochemical potential, the larger the voltage, the more spontaneous the reaction. And that's going to be because, as you'll see again, they're going to be the reactions that we're going to look at, the two half reactions, are going to be farther apart. And so the more easily reduced a substance is and the more easily oxidized a substance is, the farther they're going to be apart on chart H. And the larger the voltage that we're going to get from them is going to be. So in example number one, we're going to look at the zinc and copper half cells to see how they work. Now, we already know that this reaction from yesterday is a spontaneous reaction, and that the zinc is going to be oxidized to zinc 2+, and the copper 2+ is going to be reduced to copper metal. And so we can write those reactions in down here, zinc being oxidized to zinc 2+, and because of that 2+ charge, we're going to need 2 electrons to balance it out. And the copper 2+ has two positive charge, so we're going to need 2 electrons to balance that out to make copper metal. And we have the diagram in the right, and the copper is the cathode because it's being reduced. The zinc is the anode. So there's no question here about what's being oxidized. You can see that I've got the electron flow from the anode to the cathode. In this case, the cathode is on the left and the anode is on the right, which is backwards from what we did yesterday, but that happens. And you can see the ions are flowing also, that the electrons and the negative ions are both flowing in that counterclockwise direction, and that the positive ions are flowing in the opposite clockwise direction. Now, let's go and take a look at chart H and see how to fill in the E naughts for the oxidation and for the reduction. So chart H has a list of the standard reduction potentials. Now, these are all reduction potentials so that we can compare everything's strength as an oxidizing agent. Remember, as it reduces, it's an oxidizing agent. And so up at the top, we have the strongest oxidizing agents. Or the most easily reduced. And notice those have large positive EMFs, or large positive E naught. Okay, so the larger the positive E naught, the more easily a substance or a reduction reaction is going to occur. Now, down towards the bottom, as we come down towards the bottom, we're going to be looking at the products. So the things on the right side, we can actually think of these half reactions as being equilibrium, and so these can go in both directions. As we come down towards the bottom, in the reverse direction, so these are all for the reverse direction, we have stronger reducing agents. And a reducing agent happens because it gets oxidized. So these are more easily oxidized. Now let's find our copper and our zinc on here. Be careful with copper. We've got a couple of places where copper has a 2+ charge. We want to make sure that we pick out the copper reaction in which we've got copper being reduced to copper metal. This copper being reduced to copper 1+ isn't going to work for us. And that has an E0 of plus 0.34 volts. Now we'll put that in a moment. Hold on to that number. Meanwhile, let's come down a little bit and we're going to find the reverse reaction of our zinc. So in this case, this reaction is going in the reverse direction. The zinc is being oxidized and it has a reduction potential. This is a reduction potential of negative 0.76 volts. Now let's go back to our notes and let's put those numbers in, but there's a little modification we're going to have to make. So the copper had a potential of 0.34 volts. Because this is in the reverse direction, the oxidation is negative. We have a negative of the potential. So a reverse direction makes the sign go in the opposite direction, and negative of a negative 0.76 volts is what we're going to put in here. What that means, we put it together, and this oxidation has a potential of 0.76 volts. So this is a fairly likely reaction to happen. And when we put the two of them together, when we add them together, we're going to get the overall reaction, zinc plus copper 2+ gives zinc 2+ plus copper metal. And we just add, the plus should go here. We just add the two potentials together and we get a positive 1.10 volts. Now, I want to point something out that's very important. And we'll talk a little bit more about this down below as well. Never multiply by the number of electrons in the reaction, because the E of the cell, the E0, is actually volts per electron. And the equation that relates the E0 to the delta G0, which we're not going to use, puts those electrons in there, so we don't need to put them in here. And because this is a positive voltage, so positive E0 is the clue that this is a spontaneous reaction. Okay, so we've got this cell set up. Now, we knew what direction we were going to go in on that particular reaction. Now, let's fill in and figure out which one of these cells, which one of these half cells is going to be oxidized, which is going to be reduced, which is going to be the anode, which is going to be the cathode. We're going to label, we're going to fill in label the diagram, fill in the reactions, and calculate the E cell. So we've got gold and gold 3+, and we don't know if that's going to be oxidized or reduced, so we can't do anything yet. And we got tin and tin 2+. So let's go to chart H, and let me get rid of those markings for copper. And then let's go to look at, for the copper and zinc, let's find gold and gold 3+. Now remember, these are reduction potentials, so we'll be looking for the gold 3+ on the left. And gold 3+ on the left is all the way up near the top. Here it is, gold 3+ near the top. That means it's going to be pretty likely to be the reaction that's the reduction. So fairly easy to reduce gold, a voltage of plus 1.50 volts. Tin and tin 2+, again, be careful of tin 2 plus. There's a tin 2 plus here, but that's opposite tin 4 plus, so that doesn't work. Here's our tin 2 plus and tin metal. Now notice that it has a lower E naught. So it is not as good an oxidizing agent. It is less likely come on, eraser, for tin 2 plus to be reduced than the gold 3 plus. The other way of looking at it is easier or more likely to oxidize tin than gold. So this is the oxidation reaction. And we saw this way back in chapter 9, but now we understand a little bit more about it. This is the oxidation reaction, and that's going to go in the reverse direction, and it's going to have a potential that's going to have a negative of the negative 0.14 volts. So let's go back over to our chart. And it has fill in the diagram first, but let's put in the reactions first, and then we can fill in the diagram. So in this reaction, the oxidation we saw was going to be the tin being oxidized to tin 2 plus and 2 electrons, and that E naught was a negative of a negative 0.14 volts. Remember, we're turning that reduction potential around. And the reduction was going to be the gold 3 plus, and now you have those 3 electrons in on chart E, so on chart H, sorry, where chart E came from, and so you don't have to worry about the electrons in that case going to gold. And we have a positive 1.50 volts, and when we add them together, we get a positive 1.64 volts. Okay, 2 things we need to do. Let's add up the total reaction, the overall reaction. Now remember, in the previous lesson, I reminded you that we needed to equalize the electrons. So we have 2 electrons in the oxidation, we have 3 electrons in the reduction. So we have to multiply that by 2, and the other way around, multiply that by 3, and multiply the reduction by 2. So we're going to get, as the overall reaction, 3 tin plus 2 gold 3 plus, giving us 3 tin 2 plus 2 gold metal. And again, notice that we don't multiply the reduction or oxidation potential by the number of electrons. It just adds up. Now let's go to our diagram, and let's start labeling our diagram. So the oxidation was the tin 2 plus. So here's our oxidation reaction, which means that must be the anode. Remember, anox. And so the reduction is the cathode. So this must be the cathode. Electrons are always going to flow out of the anode into the cathode. So the electrons are flowing in this direction. And the ions, the negative ions, are going to continue in that clockwise or counterclockwise direction, which means the sodium plus is going to go in the other direction. The tin electrode is the negative electrode because it's the source of the electrons. The gold would be the positive electrode because it's going to be what's attracting those. So which is more easily oxidized? We already said that the tin is more easily oxidized. So that's the hint that's going to help you fill in these diagrams. Okay. In our next table, we've got something a little bit more, some more stuff I'm showing here as well. So we have copper 2 plus being reduced versus hydrogen hydrogen gas being oxidized to hydrogen ion. This electrode, or this cell on the right, is called the standard hydrogen electrode, the SHE. So if you see SHE, I'm not trying to talk about somebody in class. This is the standard hydrogen electrode. And if you look at chart H, you'll see that the standard hydrogen electrode, that H, is defined as a potential of 0. It's not that this has no reduction potential at all. It's that relative to this whole chart, this is in the middle. And so this has been defined as the reference cell, the reference electrode for everything. And this is how it works. This actually has, because neither one of the species in the potential is a metal, we need to use an inert metal such as platinum. So we put platinum in here to make electrical contact. We need to make electrical contact to the solution. And what we do is we pump 1 atmosphere of hydrogen gas in here. We have 1 molar, in this case, nitric acid, HNO3, in the cell, and that satisfies our need for the SHE. Now, we already said over here, you can see that the SHE has been set up as the anode, so it's going to be the oxidation. So let's write that in as the oxidation. We'll go and see in a moment that this is true. So we have the H2 being oxidized to 2H plus. Don't forget, we have to balance the mass as well as the charge, plus 2 electrons. And the reduction is going to be our copper 2 plus our 2 electrons, forming copper metal. We can write the full reaction, H2 plus Cu2 plus, giving us 2H plus and Cu metal. Now let's go to chart H, and I already found the H plus and H2. We already previously found the copper and copper 2 plus. So here that is with a voltage of plus 0.34 volts. So remember what this is telling us is, sorry about that. Yeah, copper 2 plus is easier to reduce. And H2 is easier to oxidize. And again, that's in the reverse direction. Now, we have a voltage of 0, negative 0 is still 0. So that isn't going to change sign at all. So let's go back to our notes and fill in an oxidation, the E naught of 0.00. The E naught for the copper is plus 0.34 volts. And of course, adding those together, we get 0.34 volts. And doing reactions like this, doing cells setups like this, is exactly how we would measure and determine all of these electrochemical potentials. In our lab, we're going to do something similar related to this. It's not going to be exactly this, though. We are going to set up some electrochemical cells and measure the potentials of those cells. Okay, now, in the next one, we're not even going to calculate the cell potential. You don't need to calculate the cell potential to know whether or not it is spontaneous. So what do we have? We have iron. Now, and this is not aqueous, but it's still going to help us to figure out, we do have aqueous bromine, and then we're making aqueous Fe iron bromide. And so what we have, it is aqueous, I'm sorry, my bad, it is completely aqueous. So we have Fe3 plus, and we have bromine minus. So what you've got to kind of do is figure out what's being oxidized, what's being reduced. The iron is being oxidized to iron 3 plus, and the bromine now is being reduced. I'm switching colors because going to write on the same side. The bromine is being reduced to bromide. So that's our reduction. And here's our oxidation. So let's go back to chart H and see if we can find these guys. Now, bromine being reduced is way up at the top. So let's see, let me use purple. Bromine being reduced, way up at the top. Very easy to reduce bromine to bromide. How about iron and iron 3+? Now be careful, there's a whole bunch of different irons on here, and there's two places where you're going to find iron 3+. And be careful you pick the right one again. Iron 3+ here, near the bromine, is being reduced to iron 2+. That's not the reaction we want. We want the one down here where the iron 3+ is being reduced to iron metal. Or in the reverse direction, the iron metal is being oxidized to iron 3+. And so you can see that the Fe is easier to oxidize, and Br2 is easier to reduce. That would give us an electrochemical potential that's positive because of the way this is set up. And so even without having to calculate it, we can come back and we can say it is going to be spontaneous in the forward direction. And again, Fe is easier to oxidize than bromide. You always have to compare the two things that would be either oxidized or reduced. And Br2 is easier to reduce than Fe3+. All right, last thing. You can apply the ease of oxidation without even knowing the potentials. And I'm going to tell you that the following reaction with fictional elements, that's not boron, that's a fictional element B, is not spontaneous in the forward direction. But what that means is that it is spontaneous in the reverse direction. Now let's look at A and B, because my question here is which is more easily oxidized, A or B? So A is being oxidized in the forward direction, and B is being oxidized in the reverse direction. So since the reaction is spontaneous in the reverse direction, that means that B being oxidized, this is the more spontaneous reaction, and that means B must be more easily oxidized. And so we'll have some questions in the homework on that as well. All right, I hope this is clear enough, and we will go over this in class next time. See you then.